nanohub.org.
Online simulation and more for nanotechnology.
Hi everyone, I'm Zhiqiao. Manan and I are PhD students in mechanical engineering at the University of Illinois, Urbana-Champaign. Today, we will work together throughout this tutorial to introduce Gaussian process regression for surface interpolation. We will begin with an example providing some motivations for surface interpolation and Gaussian process regression, or GPR. Then, Manan will take over to introduce basics of GPR. After that, I will explain how to apply GPR to surface interpolation. Finally, I will introduce the GPR-based interpolation technique called filtered Kriging to improve interpolation performance. First, we are providing a motivating example. There are many cases in science and engineering where we are interested in fine-scale characterization of some quantities over surfaces. For example, in nanomanufacturing, we make structure at very small scales. To examine quality of the manufactured part, we need to measure the height over the surface at a very high resolution. Let's look at a more specific example, which we will use later today to demonstrate the methods. Surface in this example is manufactured by two-photon lithography, which makes use of two-photon polymerization to fabricate three-dimensional complex microstructure and a sub-nanometer resolution. On the surface, there are 5 × 5 repetitive hemisphere structures with 7.5 micrometer between adjacent center, as shown in this figure. The measurements are taken at a very high resolution of about 95 nanometer per pixel. In many cases, it can be very difficult to actually measure surface at such a high resolution because physical measurements could cost a lot. For example, it could be time-consuming because of so many data points to measure. Also, the instrument capable of such high-resolution measurement itself could also be expensive. If we hope to reduce the cost, often we will have to sacrifice the quality of measurement data, which means that the raw measurement data generally has low resolution, as shown in the figure on the right, and we may not measure all locations we are interested in. This motivates us to use interpolation. If we take a relatively broader sense, an interpolation method draws estimation from surrounding or nearby measurements, which means that it can be used to inquire values at unmeasured locations. So, interpolation can be used to fill missing values, or more specifically, in our example, we will use it to generate a high-resolution surface estimation, as shown in the right figure, from coarser measurements, which can be obtained at a lower cost. As we have just mentioned, interpolation makes estimation from measurements. But this problem it addresses can be formulated as a regression problem in statistics. We prefer this viewpoint because it allows us to adapt to data and borrow methods from statistical toolbox, including the Gaussian process regression we are introducing today, which is a very flexible tool for regression. And Manan will take over to introduce some basics of GPR.
So Zhiqiao introduced the problem of spatial interpolation for TPL manufactured surfaces and sort of how we can use Gaussian process regression or GPR in order to solve it. But first, let's take a step back and understand what Gaussian process regression or GPR means. And I'll sort of explain that using this simple sort of 1D example to motivate the use for GPs. So GPs are a very flexible tool for machine learning in general. And so we'll first go over that and then come back to the TPL problem that Zhiqiao talked about and see how it can be applied to this problem as well. So consider this 1D example where I have 3 points, x1, x2, and x3, and the heights at each of these 3 points, h1, h2, and h3 is given to me. And the task here is that given these x's, I want to model these heights h. In order to do that, I'm going to assume that my model h follows a multivariate Gaussian distribution. So the heights h1, h2, and h3 follow a joint Gaussian distribution with zero mean for simplicity right now, and some covariance that I represent with covariance matrix C. Now the question becomes, how do I model this covariance matrix, or how do I model this individual covariances C, I, J? And there is this notion of spatial similarity in interpolation, where we want to say that points that are closer to each other are sort of more correlated as compared to points that are further away from each other. And this covariance is exactly what measures the strength of that correlation. And so we can represent the covariance Cij using an expression roughly like this, which is an exponential of the negative distance squared, where this Cij goes to 0 as the distance between xi and xj increases, or they move further and further apart. And it is high, or it is at the maximum value of 1 when xi and xj are essentially the same point. So this is how I can sort of fulfill my first goal, which is to model the statistical correlations in my observed data. Next, say I have this observed data and I have this unobserved point x star, and I am asked to calculate the height or the expected height at that point x star. In order to do that, say I give you 3 possible points, 1, 2, and 3. Then most of us would intuitively pick point number 2 as the best candidate. And the intuition here is pretty much what the intuition was in the earlier slide, which is that because x star is kind of in the middle of x2 and x3, then h star can fall somewhere between h2 and h3. And similarly, we can capture this intuition by now jointly modeling the observed heights h1, h2, h3, and h star as a normal distribution with, again, zero mean for simplicity, and then some covariance where this part of the covariance comes from the observed data. And now we have this another sort of vector of the covariances between the observed and the unobserved data that I'm going to abbreviate using C star and C double star, these two matrices. Once I have my heights in this formulation, then getting a distribution for h star is fairly straightforward because there are rules for conditionals of multivariate Gaussian distributions. And so I can say that the distribution for h star, given all this data and given this height h, is a multivariate normal distribution with some mean and some standard deviation. So this mean can be the expected height h star at that point, and the standard deviation kind of gives you the confidence with which I can say that the height is h star. To go from this to this, you can consider that there is this very simple formula that you can simply look up. For interpolation, though I don't need the height at only one point x star, I kind of need the height at each and every point in the domain. And so to extend this in a straightforward manner, I can consider that x star moves from the first point on this axis in minor intervals all throughout the axis. And at each point, I'm sort of repeating this calculation in order to get something like this, where now this blue line indicates this, the height h star at that point, and this green line indicates the confidence with which I can, or the prediction uncertainty that I have at that point. So when I start modeling, I have some prior belief about what my data should look like. For example, my covariance can be modeled using a negative squared exponential like we saw in the previous slide. So there is some prior notion as to how I want to model the data, and that can be captured in the prior distribution here. And as I start observing data, as I start observing x1, x2, and x3, that belief in my prior starts to change, and that change is reflected in the posterior distribution. So these are two terms that we'll see later in the demonstration as well. So the posterior distribution has a posterior mean, which is the value of the interpolated result at different points, and a posterior variance that tells us how certain we are about our prediction results. So a generalization of this simple example that we just saw is termed a Gaussian process, which is a collection of random variables, any finite number of which have a joint Gaussian distribution. So in the previous case, we saw how the observed heights h1, h2, and h3 and the unobserved height h star followed a joint Gaussian distribution. A GP is completely specified by its mean function, which is m of x, and the covariance function c. And sometimes for notation, we write h, instead of writing it as a GP with mean m, we take the mean out and write it as some mean function m of x plus zero mean GP, because sometimes if you have zero mean, then it has some advantages or ease of modeling. This is also the notion that Zhiqiao will use later in his TPL example. Let's take a closer look at the covariance function that we use to model our data. So this covariance is modeled as a parametric function usually. The example that you see here is called the squared exponential kernel or squared exponential covariance. Notice that this function is exactly the same that we used in the example to begin with, except that now I have introduced this additional parameter called delta square, which I call the length scale hyperparameter. Now this delta square governs the properties of the underlying functions, but this is what we visually mean by that. So we introduced the prior distribution earlier, and imagine that you are sampling some points or sampling some functions from the prior distribution. When you have a very small length scale, the functions kind of look very rough, and they start to smoothen out as you increase the value for delta. So this plot kind of makes it clear why delta is called the length scale hyperparameter, because it controls the distance at which the covariance sort of drops off for any two adjacent points. In order to model data, you can use other covariance functions as well. We are just showing this one very common one for an example. But there are many other covariance functions out there. In fact, there are books written on covariance functions. So if this may not be the best fit for your data, then some other covariance function might be. Finally, let's look at how we can put everything together in order to generate this end-to-end workflow using GPR. So step one, obviously, is you observe some data that you want to model. In this case, you observe, say, 6 points for which you have the coordinates and the heights available. In step 2, you specify a GP model. And by that, what we mean is you specify the mean function M and the covariance function C that you want to use for the GP. So for example, I can say I want to use a zero mean GP with squared exponential covariance. You then use this model and fit this model to your data. This means that you choose the value of the hyperparameter, in this case delta, that best explains your data. So in this case, the first two plots, you can kind of see an overfit and underfit happening for lower and higher values of delta. But for delta equal to 1, you see a good fit. And so you would choose this model. And once you have that model in place, you can calculate the posterior mean and variance. And this posterior mean essentially gives you the interpolation result between 2 points. Again, relating back to the TPL example, we can kind of take this intuition there as well, where here we did things in 1D because it's easier to visualize and understand GPs in 1D. But in that case, all your observations that you see here will essentially be measurements that you take on that 2D surface. And this interpolation that we see here as a 1D line will essentially be a 2D surface that you reconstruct from it. So the intuition stays the same. You can generalize it to 2 dimensions, 3 dimensions, or n dimensions for that matter. So this was some basic introduction to GPR. Now we can move to the NanoHub tool. Go to that link and you might have to log in order to launch this tool. And when you launch it, you will reach this page here. And for this part of the tutorial, we are just going to use a simple GP example in order to recreate some of the plots that we just saw and like to show you how you can work with GPR in Python using, say, your own data. And if for some reason you cannot open the tool, then don't worry. I'm going to go through the entire code on the screen anyway, so you can just follow along with me. So I'm going to go ahead and get started. This is a Jupyter notebook where each cell that you see runs some Python code. And you can run each cell by using the run icon right here, or you can press Shift plus Enter. So in the first cell, I'm going to import a couple of Python packages, NumPy and Matplotlib. Matplotlib helps you plot stuff, and NumPy deals with matrices and arrays. So I'm going to run this. For the purpose of this demonstration, I'm going to say that the function that I want to model or interpolate is this simple function h of x is sin x plus x by 4 in this domain -5 to 5. So this is just for demonstration purposes. In this cell, I'm going to define this function, and then we can visualize it. So this is what the function looks like in this domain -5 to 5. Once that is done, I'm going to define the covariance function for the GP. This is exactly the squared exponential function that we saw in the slides with one hyperparameter delta square. And this cell defines this covariance function for us. I have written it in a more general sense so that if you have multidimensional data, you can still model it using this function. But for the purpose of this case, we can just assume that it takes in two parameters, x1 and x2, or 2 points, and a value for delta, which is the hyperparameter, and gives us the covariance between any 2 points. Finally, this function is the most important function for this notebook, which is the simulate GP function, and it takes in two arguments, n and delta. N is basically specifies the number of points that it randomly observes on your domain, and then uses this kernel hyperparameter delta that you supply in order to simulate a GP. Now, by simulating a GP, what we mean here is three things. First, we want to visualize the prior distribution, visualize the posterior distribution, and finally see the interpolation results. So plot the posterior mean and standard deviation. I'm not going to go into the details of how it does this in the interest of time. There's a lot of comments that you can follow along, or we can talk after the presentation as well if you're interested. So I'm going to go ahead and run this. So first, let's start off by simulating a GP that does not see any observations in the domain. So I'm going to simulate a GP with n equal to 0 observations, and let's fix the delta value to 1 for now. I'm going to run this, and this is what we observe. So in the first plot, you see 10 random samples from the prior distribution, 10 random samples from the posterior distribution, and finally the posterior mean or the interpolation result. Two things to observe here, that the prior and the posterior are exactly the same. And that is expected because if you recall what the prior was, it is your prior belief in the data, and this is how that prior belief changes. Now, if I have no data, then there is nothing for the belief to change, and so both of these are exactly identical. And similarly, because there is no data, there is nothing to interpolate, and so this assumption of zero mean GP kind of holds throughout the domain. So I just don't see any points, and so I have 0 across the domain. Next, let's see what happens when we observe 1 point in the domain. So I'm going to simulate a GP with n equal to 1 observation, keeping delta the same. So the prior still stays pretty much the same. It still doesn't get affected by the data point, but the posterior now starts getting affected, and all the samples that you see in the posterior pass through this 1 point that you observed now. And similarly, the posterior mean also changes to account for this point. And notice how the prediction uncertainty or the variance decreases at that point and then increases again as you move away from the point. So this is one way for GPs to tell me that I see an observation here, so I'm certain of what I see here, of what I've modeled here, but everywhere else it's still uncertain. And in that regard, let's say we simulate 5 points one after the other and see how the GP changes in each point. So this is for 0 points, 1 point, 2 points, 3 points, 4, and 5. So in each case, the prior still stays the same and doesn't get affected by the data. The posterior in each case starts passing through the data points that you see. And similarly, the posterior mean kind of accounts for that. And you can see that the posterior mean starts approximating the actual function, which is sin x plus x by 4, better and better as you start observing more data. In all of these cases, we fixed the hyperparameter to 1, but let's see what happens when we change the hyperparameter. So say I'm going to simulate a GP with 5 points and a higher value of delta equal to 10 and a lower value equal to 0.2. Again, these are the two plots that we saw in the slides, that here it's overly smooth, whereas here it's overly rough. And that leads to underfitting in this case and overfitting of the GP in this case. So both of these models don't have good expressivity for the kind of data that we observe. And so this raises the question, how do you choose delta? Like, how do you optimize that hyperparameter? And luckily, we don't have to do it manually. Python actually does it for us. And we can use the scikit-learn package in Python in order to do this. Scikit-learn is a machine learning library in Python that does all the basic classification and regression tasks. And from scikit-learn.Gaussian processes, I'm going to import the Gaussian process regressor. So this is the class that helps us fit and model GPs easily. And scikit-learn also offers you a lot of kernels so that you don't have to define your own covariance functions. So the covariance function that we've defined above here, it's actually automatically imported from scikit-learn as an RBF kernel or radial basis function kernel. So I'm going to run this, which will import both of these for me. We can then define our own kernel, as my kernel is an RBF kernel with some length scale and some length scale bounds. So what this does is basically, when you optimize delta, it asks scikit-learn to search in this range. So it only looks for values between 0.001 and 1000. I'm going to run this. And so it says that my kernel parameters are one length scale, that you start off with a value of 1 and then optimize in this range. In this cell, I'm just going to resample the data that we did for the earlier case study and store it. And finally, I'm going to declare GPR as this Gaussian process regressor that has this kernel that I've defined here, and then run GPR.fit. Now, when I do that, scikit-learn automatically identifies what the hyperparameter of my kernel is and optimizes it for me. And so I can print what the optimum value is if I run this. So when it fits the data, it automatically says that the optimal kernel found is RBF with length scale this, and the optimal length scale or the optimal value for delta it found is 1.878. So we've been using a value of 1 before, but that even wasn't the mathematical optimal. The mathematical optimal for this case is 1.878. Finally, you can call GPR.predict in order to get the posterior mean and the posterior variance or standard deviation. So you don't have to write any code for it. You just do GPR.predict and it automatically gives you the posterior. So go ahead and plot that. And so this is the ideal interpolation result for the example that we saw earlier. So that's pretty much it for a basic introduction to GPR. This is a very brief intro, but hopefully it kind of gave us an intuition as to what GPs do and what happens under the hood. And we'll take this intuition and some covariance function concepts that we saw in this tutorial, and I'll let Zhiqiao continue with his 2-photon lithography example and see how more advanced methods sort of fit in that case.
Okay. So as we have just seen from Manan's introduction, GPR can be used to draw estimations from samples, which means that it can be used to do interpolation. GPR-based method, when used for interpolation purposes, is also known as the Kriing type methods. So we will refer to this name later. And to use Gaussian process regression for interpolation, we model the surface with a Gaussian process. Here, the h is a quantity we are interested in over the surface, for example, the height. And here, the x is a two-dimensional coordinates over the surface. As before, this is a Gaussian process with mean m and covariance function c. And we write it as the sum of the mean, which generally captures the large scale global trend, and the other term eta, which is a zero mean Gaussian process with covariance functions specified, generally captures some small scale local variation. And to use GPR for interpolation, we follow the same workflow. First, we obtain some measurements of the quantity, for example, the height, or a set of locations, which is the uppercase X here. And then we select a Gaussian process model. Specifically, we need to specify the form of M and the covariance function for eta. Then we feed the model to the data, and we can further make inference to obtain the estimations. Next, we will introduce the classical approach for fitting the model to the data. So that this classical approach is more suitable for spatial interpolation purposes, where we generally have a lot of data points. So the classical approach for fitting the model, recall that the covariance is purely related to the eta, to the local variation term in our Gaussian process model. So the classical approach first make a provisional estimation of the mean or the trend. Then it subtracted that trend, a provisional estimation of the trend from the measurements to obtain an estimation of the variation eta. And classical approach assumes that the covariance is stationary, which means that the covariance, which captures the similarity between locations, only depends on the difference of their coordinates. This assumption allows us to compute an estimation for some spatial differences for the covariance function. And with this estimated covariance, together with the specified parametric covariance model, we can fit the model to the estimations to obtain the final fitted covariance model for interpolation purposes. Different Gaussian process regression-based methods deals with the trend in different ways. And we will adapt two conventional methods below for the TPL datasets. The first one is ordinary Kriging, which assumes the mean to be some unknown constant. The second one is Kriing with external drift. So KED assumes the mean to be a linear combination of a few known basis functions. Because our TPL surface is near periodic, so we use 25 trigonometric functions with the same period for that basis. Both ordinary Kriing and KED fit the basis function to the measurement data to obtain the provisional mean estimation. The new technique we will introduce is called filter Kriing. So filter Kriing self-resolves the global trend not by fitting, but using a filter. That's why we call it filter Kriing. Then the residual can be modeled and estimated separately. Finally, we merge the estimation of the eta and the estimated global trend together to obtain our estimation. In some cases, it can be more effective than the standard Kriing methods like ordinary Kriing or KED. This is especially for periodic cases, and we will try this on the GPR manufactured surface, which is the example we have mentioned at the beginning. Before we actually go to the notebooks, we kind of explain why filter Kriing could improve the covariance modeling. To understand this, we need to explain a common assumption made by conventional covariance models. Recall that we already assumed that the covariance to be stationary, which means that the covariance between different locations only depends on the difference of their coordinates. Common covariance model makes some further assumptions about the isotropy, which is stronger, and it means that the covariance depends only on the distance between locations instead of the difference of their coordinates. So the left figure showed how some common isotropic models, how their covariance varies with the distance between locations. And on the right figure, it depicted how some isotropic models actually vary with respect to the two-dimensional coordinate difference. And we then we can come back to compare different GPR-based methods. Recall that different methods deals with the global trend and local variation in different ways. And with different assumptions about the global trend, the local variation can display different properties. We can see from the figures in the first row, in the first figure, ordinary Kriing assume the constant trend, which captures no periodicity. So their local variation is still strongly periodic. And for KEB with trigonometric basis, it could capture periodic components with a trend, and filter Kriging preserves even more periodic components with a filter. And we can see that there are almost no periodic pattern in the residual for the filter Kriging. Consequently, this different local variation eta has different covariance structure. Recall that the covariance captures the similarity between different locations. So we may expect that the covariance have similar periodicity as the local variation at that eta. So this intuition can be confirmed by looking at these figures in the second row, which are the covariance we have estimated from the local variation. And we can see that if we recall the isotropic covariance models we have mentioned before, we can see that this periodic pattern cannot be well captured by isotropic models. And we can see clearly that after filtering, the periodic component is almost eliminated, and we can expect that the filtered residual can be better modeled with isotropic covariance functions. And the goodness of fits with the isotropic covariance model can be visualized more clearly in the following figures. In the figures, the green dots represents the empirical covariance, but we map it along the radial direction. The blue line indicates represents the average of the green dots in some small bins along the radial direction. The stronger the green dots scatter around the blue line, the less isotropic the actual covariance structure is. So we can see clearly that the ordinary Kriing cannot be well modeled with any isotropic covariance function. And for KEB, because the periodic component is kind of reduced, it can get fit better, but still not very ideal. We can see that there are still some very outliers. And in general, the filtered results can be well fitted with isotropic model compared with these conventional methods. And yeah, the orange line is a finally fitted isotropic model. And so we will go to the Jupyter notebooks, and you can go back to this page and click this tutorial for filter Kriing and open this page. And we will just go through all the procedures we have introduced in this Jupyter notebook. Before we actually start, you can click this cell and run all the cells. So because there is one block that can take some time to run, so I suggest running all before we start. And the first block just add some self-defined functions, the MATLAB path. Yeah, the code they are using for filter Kriing is written in MATLAB instead of Python. And in the second part, we just import the data, and this block generates a figure that depicts the first surface in that GPL dataset. In the second part, we downsample this data set to simulate the low resolution measurements. We downsample the data uniformly in each, every 5 points in each direction and store it in this structure and store the ground truth. And in this block, we will store some intermediate results and visualize. We can visualize the downsample data running this block. And you can get this figure. The left one shows the high resolution measurements, and by downsampling, you get the blurry version on the right-hand side. The third part of this notebook just introduces standard GPR-based methods for spatial interpolation, including the ordinary Kriging and the KD with trigonometric basis we have mentioned in the slides. And these texts, I am not explaining this in details. I think these texts can provide you with sufficient technical details that you need to go through all the code. And we specify the range of the coordinate distance that we need to compute for the empirical covariance. And in this block, we compute the empirical covariance for ordinary Kriing. And these are computed using this empirical code from 2D function, which I wrote it. Identify the trigonometric basis function basis and fit the basis the data using ordinary least spheres, and we can obtain the estimation of the local variation, the estimation of eta, and it is plotted in this figure. After after computing this estimation, we can further estimate the empirical covariance for KD, and it will be displayed in this one. In the fourth part, we go into the filter Kriing. So first, we create a bandpass filter that allows the periodic component with the same period as the TPL surface to pass. The filter is just a very convolutional filter, which takes the sum of the height at different locations, and the weight in that sum is visualized in this figure, where the strength of the weights are represented with the color and size of these dots. And here I added a brief explanation why this filter results in a bandpass filter. So you can refer to this later. Because at the moment, we are still unable to apply this filter to the measurement data because there are many missing locations. We don't know the value. So before applying the filter, we first use a very rough interpolation result. Here we use the standard bicubic interpolation to interpolate the results. So we can apply the filter to the interpolated results to estimate that filter trend. Applying that filter to the pre-interpolated results, we get the trend estimation in this data, and we can subtract that estimated trend from the measurements to obtain the residual, as depicted in this figure, and further compute its empirical covariance like this. And finally, in the last part, we will compare the performance of the different methods. First, we specify the parametric covariance function, which are all isotropic and kind of common for the Gaussian process regression. And this block specifies this parametric function. And we visualize what this looks like. And the next block generates the visualization for them with respect to the two-dimensional coordinates. And finally, and in the next block, we fit the covariance function to the estimated empirical covariance using this core fit isotropic function for different methods. And we can visualize the results, we can visualize the goodness of fit in these figures. Finally, we can compute the estimations using this Kriing function, and we can obtain the final results. This block takes a while to run, so after obtaining all the results, we can compute the root mean square error by comparing it to the ground truth. And we can see that the ordinary Kriing actually failed in this attempt because it kind of goes outside the capability of the isotropic models, and which makes it even worse than the bicubic interpretation. And finally, we can see that the filter Kriging actually outperforms all other models. And that's all for the presentation for this tutorial.
Yeah, thank you very much for a great presentation.
I see one question in the chat that I can answer.
Go ahead, please.
So the question is there any requirement on the number of sampling points required to start? And I'm guessing this is in relation to the very basic GP example that we discussed, and not really. You can, like we saw in the code, you can also have 0 points and have the same prior and posterior. With no interpolation, you can even interpolate with 1 point, except that if you have like very few points, then your interpolation results will not be very good. So as you increase the number of observations, the quality of interpolation keeps increasing. But like mathematics, no, you don't need any minimum number of points to sample from.
All right, I see another question came in via Q&A. What was the procedure for designing your empirical covariance function?
So there are many estimations for the covariance function, which you can actually refer to the classical textbooks. If we if we assume the stationarity of the process, you can actually just compute I can share the screen to show the formula for this estimation here. So because eta is zero mean and stationary Gaussian process, so and the and you can simply use this equation to compute the empirical covariance. You can see this very clearly because this C is basically the expectation of this one. It's just very straightforward to see that this is an unbiased estimation. Although there are some very more robust estimation for this, I am taking this one for simplicity. And this is sufficient for our purposes because we have enough data points.
Great, thank you. We do have another question. What is the difference between kernel ridge regression and GPR?
I think kernel ridge regression can be reformulated as a special case of GPR, in which if I remember correctly, you assume that you assume some merit. If you compare it to the model we have here, you assume some additive Gaussian error in your measurements, which kind of makes some regularity in the kernel ridge regression. And the kernel is some corresponds to the covariance function we have used in the Gaussian process regression.
I see one more, I think, previously unanswered question, which is how do we consider the prior function just by observing the data set? So that's a great question, because choosing a prior is very kind of like choosing a kernel is important for GPR. And part of it comes with intuition as well. For example, if you have, say, a periodicity in the data like TPL, then you have specific kernels for that. If you have very smooth functions, you have kernels for those, and so on. Kernels can also be multiplied or added together to form new kernels. And so once you observe data, sometimes like the more you use GPR, the better you will get an understanding of what types of kernel you can use. You will have an idea of what the prior distributions look like for different kernels, and that will help you choose. And if you don't know it, then you can maybe use a bunch of different kernels and see which one fits your data the best possible manner. So it's like using different neural network models in order to see what gives you the best training error, for example. So it's more of an sort of empirical process than like a strict theoretical framework.
Great, thanks. We had another question come in the Q&A. Can we do extrapolation with GPR?
Yeah, we are able to do some extrapolation, but if you get too far away from your merit points, the estimated result can be very unreliable. And you can kind of confirm this by computing your posterior variance, as shown in Manan's slide.
You can see in on the examples given that when you start extrapolating, the uncertainty essentially diverges. So the further you go out, the riskier it becomes.
Yeah, and that is one of the most important properties of Gaussian processes too, that it not only gives you the estimation at a particular point, but it also tells you the uncertainty at that point. So you can really judge how confident you can be at a particular point, which very few other methods have that ability.
Exactly. That's very important for decision making, when you need to know not just the value, the expected value, but also how much confidence you have in it. Thanks everyone for coming, and thanks again to the speakers for a great tutorial. Thank you.